Basalt is a fine-grained volcanic rock that forms when lava rich in iron and magnesium cools quickly close to the surface of a planet or moon. On Earth, basalt makes up most volcanic material, accounting for over 90% of all erupted volcanic rock, and erupts at roughly 20 volcanoes annually. Its presence extends beyond Earth, covering vast regions on Venus, filling lunar lowlands and blanketing wide parts of Mars. The lava that produces basalt moves quickly and spreads far, as its low silica content keeps its viscosity relatively low, causing extensive lava flows that can build up massive plateaus called flood basalts. The chemical structure of basalt reflects its origin deep within Earth, typically from melting in the upper mantle. This magma rises through decompression caused by tectonic movements. A volcanic rock is called basalt if it contains less than 52% silica, little feldspathoid or quartz, and plagioclase is the dominant feldspar. Basalt tends to be dark gray or black due to an abundance of dark pyroxene minerals, though some types are pale if they contain high levels of plagioclase. When the rock includes numerous gas bubbles trapped during solidification, it is termed scoria. The density of basalt averages about 2.9 grams per cubic centimeter, higher than granite. It sometimes shows larger crystals embedded in finer material, known as a porphyritic texture, with minerals such as augite or olivine forming first as the magma cools. In some regions, column-like structures may develop when large amounts of lava cool slowly, producing distinctive landforms such as those found at the Giant's Causeway. Variations in the chemical makeup of basalt reflect its environment of formation, with different types, such as alkali basalts or tholeiitic basalts, associated with oceanic or continental settings, rift zones, volcanic arcs, or mantle plumes. For example, mid-ocean ridge basalt found along Earth's ocean ridges is distinguished by the scarcity of certain trace elements, hinting at diverse mantle sources. The word basalt traces back to Latin and Greek, related to hard stones used as touchstones. The current meaning took root in the Renaissance, notably through the scientific writings of Georgius Agricola. Over Earth's long history, early volcanic rocks often contained even less silica than present-day basalt, giving rise to rare rocks like komatiites due to the different chemical conditions of the planet's youth. Over time, as crustal processes evolved, basalt became one of the primary materials shaping planetary surfaces in the solar system. Basalt is predominantly composed of calcic, plagioclase, feldspar, and pyroxene, with olivine sometimes forming a substantial part of its makeup. Minor minerals include iron and iron titanium oxides, such as magnetite, ulvospinel, and ilmenite. These oxides let basalt acquire distinct magnetic properties upon cooling, which have made it a frequent target for paleomagnetic analysis. Tholeiitic basalts feature pyroxenes like augite and either orthopyroxene or pigeonite, alongside calcium-rich plagioclase as phenocrysts. Olivine may also occur and can be rimmed by pigeonite or pyroxene. Ground mass minerals occasionally include silica forms such as quartz, tridymite, or cristobalite, yet olivine is rarely present in the ground mass. Alkali basalts, in contrast, often lack orthopyroxene, but have olivine and feldspar phenocrysts that range from labradorite to andesine, while their augite contains more titanium. Their ground mass might feature minerals like alkali feldspar, leucite, nepheline, sodalite, phlogopite mica, and apatite. Basalt has relatively high temperatures for both melting and solidifying, roughly 1200 degree Nax for the liquid phase at the surface and about 1000 degree Asaj for the onset of crystallization, topping values of most other common igneous rocks. Tholeiitic basalts usually form at mantle depths of 50–100 kilometers, while many alkali basalts can originate at greater depths, perhaps reaching 150–200 kilometers. The development of high alumina basalt, with its notable aluminum content, remains debated. Some suggest it is primordial, while others attribute its formation to processes acting on basaltic melts. Geochemically, basalt is marked by high magnesium and calcium oxides and low silica and alkali contents, fitting its established classification. It generally holds between 45–52% silica by weight, modest total alkalis, a small percent of titanium dioxide, higher iron oxide, and notably high alumina. calcium levels typically hover near 10%, and magnesium stays within 5 to 12%. High alumina variants can reach up to 19% aluminum oxide. Mafic rocks related to alkali basalts may reach unusually high alkalis, sometimes above 12% when sodium and potassium oxides are summed. Differences exist between basaltic subclasses. For example, mid-ocean ridge basalts, MORB, tend to display low alkali and rare earth element levels compared to alkali basalts, which are richer in light rare earth elements and other incompatible elements. The compositions of MORB can vary geographically, and they have formed a foundation for deciphering tectonic processes. Isotopic studies examining elements like strontium, neodymium, lead, and noble gases provide insights into mantle evolution. The parental rocks for basaltic magma likely incorporate both peridotite and pyroxenite. Basalt's texture and appearance record the environment of its eruption. Above ground, basalt emerges in several forms, from scoria and cinders to extensive lava flows. Vesiculation is common at flow tops, imparting a low-density, frothy aspect, frequently tinted red from iron weathering. Varieties like Ea and Pahoho describe blocky and smooth, ropey lavas typical in places such as Hawaii. Lava tubes often develop in Pahoho flows. Explosive outbursts can produce tuff or breccia under rare circumstances, like lava blocked in a volcano's throat-building pressure from trapped gases. When basalt cools as thick flows, it develops contraction cracks which often shape hexagonal columns, the size of which correlates with the cooling rate, a hallmark structure observed in well-known locations. Underwater, the depth dramatically affects basaltic eruptions. At significant depths, pressure curtails volatile release, most lava solidifies quietly, and pillow structures hallmark the rapid cooling of lava in contact with water. These rounded pillows encased in glassy rinds demonstrate the eruptive process underwater or beneath ice sheets. Some eruptions, often in shallow water or near the surface like Surtse's Birth in the Atlantic, begin explosively but evolve into fluid, sheet-like lava advances. On Earth, basalt covers the majority of volcanic terrain, dominating oceanic crust and many oceanic islands. It is common throughout significant continental flood regions, such as the Deccan Traps or Columbia River Plateau, and is widespread across volcanic arcs where crust is thin. Precambrian basalts now mostly appear metamorphosed in regions known as greenstone belts, which are dotted by green-colored minerals formed during low-grade metamorphism. Beyond Earth, basalt characterizes much of the Moon's Maria, as well as landscapes on Venus, Mars, Io, and Vesta. Lunar basalts stand apart from terrestrial ones with higher iron and variable titanium levels. They also lack the hydration and oxidation typical of Earth basalts and often reveal shocked structures from meteorite impacts. On Venus and Mars, surface exploration and meteorite data both point to widespread basaltic lavas, while Vesta's crust appears layered with basalt, supporting its proposed link to certain meteorites. Calcium released by weathered basalt reacts with atmospheric carbon dioxide and forms carbonate minerals, contributing to long-term carbon sequestration. When subjected to high heat or pressure, basalt transforms into metamorphic rocks, such as green schist or amphibolite, providing clues to the metamorphic history of regions and sometimes hosting economic mineral deposits. In underwater settings, the interaction between basaltic rocks and microorganisms is pronounced. Certain bacteria can exploit reduced iron and manganese in basalt for metabolic energy, influencing the exchange of elements between rock and seawater and highlighting the potential role of volcanic settings in early life's emergence. Historically, basalt has been used as a construction material, for cobbles, and for sculpture, as well as in the manufacture of insulation products like stone wool. Recent studies have considered basalt's potential in trapping carbon dioxide, particularly in underwater environments where water can prevent its return to the atmosphere.